Our last three theorems. So we're going through the theorems, right?
Yes.
Line from the center to the perpendicular to a chord. Angle at the center twice the angle at the circumference. Semicircle, I'd like a choir. Bow tie, but please don't say bow tie, it's angles in the same circle segment. Then it's the cyclic quads. Opposite angles are supplementary, exterior angles equal to the opposite interior. Then the last three are all about tangents. Now what is a tangent? Because it's a funny word. In Afrikaans it says raak lyn, so the line raak. But a tangent doesn't say what it does. A tangent is a line that touches the circle. If it's a little bit further away, it won't touch. If it goes any closer, it'll not be a tangent, it'll be a chord. It'll touch right through. It'll cut on two places. Are you with me?
Yes.
So a tangent just touches. Now the three tangent theorems are theorem number 7. If there's a radius, so again you've got to have the center of the circle, are you with me?
Yes.
So whenever I give you a big sum eventually on this, and there's a center of a circle, you know a few things about it. Theorem 1, Theorem 2, Theorem 3, Theorem 7, now in this case, will all have to be a center of a circle. If this happens, if you have a radius, in other words, right, because it is an angle at the center of the circle. No, I'm talking wrong. Line from the center of the circle to the tangent will then be perpendicular. The abbreviation is radius perpendicular to tangent. Now if you say tangent perpendicular to radius, would that be wrong? No. Okay. So this will then be 90. Always, you can see all of the things popping out. If there's a 90, there could be a triangle, there could be a Pythagoras, all the stuff that can pop out there. But whenever there is a tangent, and there's a radius drawn to it, there will be a 90-degree angle. So if there was a 90-degree, what did I know about this line? It will be a tangent. I'm talking about opposites, converses. If I didn't tell you it was a tangent, and there is a 90-degree angle, you know that it is. So there's going to become sums later on. That's going to be somewhere, and I'm going to say, aha, this is 90. Then you're going to tell me that that could have been sucking this out of my thumb and it's not working. But if there is a 90-degree angle, it can be that it's a tangent to some circle somewhere that was drawn in your sketch. I'm trying to make you see that it's going to be a little bit outside the box thinking, without an actual circle there. You'll be told, okay, let's see if you can prove that it is a tangent. If there's 90, then it will be a tangent as well. Okay, but radius perpendicular to tangent. Will you be able to see that?
Yes.
I think so. But there has to be a radius. Then it will be 90. With the more difficult stuff, the converses will be there. Theorem 7. Theorem 8 is also about a tangent, but this time, there's two of them. Now, I call this the party hat. Because, you see it? Please don't do that in a test, but the party hat means that these two pieces there will be equal in length. The theorem says, if you draw two tangents, now if I want to draw a tangent to that thing, then it can go either this way, touch, oops, it's very skewed, and that way as well. With me? No other tangent from that point. Can't be. It won't cut. Do you agree with me?
Yes.
So if I go anywhere outside of the circle, and from that point I draw two tangents, one to the one side, one to the other side, they will be equal in length. That's the theorem. So if there are two of them, then you will know that those two pieces are equal. Can you see all the stuff about isosceles triangles maybe coming in here, all the stuff? Okay. And then I'm saying that the abbreviation for that, if two tangents are drawn outside a circle to the circle, they will be equal. Just two tangents from a point outside of the circle. Two tangents from a point. That's the abbreviation. What I do want to say here is not really a alternative or a variation, but very often this goes along with congruency nicely. Not in my sketch here with the party hat there, but in my sketch, if I do draw the, what are they? Radiuses to the points of touch, the tangent touch, then this will make up for two congruent triangles. Always. How come? Radii, common, and then the theorem you've just done. Those two lines will be equal because of the party act, right? So they will always be congruent if necessary. It won't always be there, but often it's a possibility that there can be congruency in the whole mix of things. Also, there's so much other reasons for congruency, because that will also be 90 then, right? Because of theorem 7. This is what we call Euclidean geometry. The next theorem builds on the previous theorem. So I've just done 90 degrees, so here I'm using it. Are you with me? Okay, so that's how they build upon each other. But keep it in the back of your mind, there could be congruency in the mix of things. And congruency means you've got to know your four reasons. Side, side, side. Side, angle, side, which means the included angle. Two angles and a corresponding side, not just any side, corresponding with the angles. And then the fourth one is just for 90-degree triangle, hypotenuse side, another side, and 90 degrees. Can the other three also be used in a 90-degree angle triangle? Yes. But the 90-degree triangle reason can only be used for the 90-degree triangle. Are you with me here? Yes. You know a heap of things already. Congruency is one of them. The last theorem, the last tangent theorem, is maybe the most important one. And I'm going to teach you, when you see that your sum has a tangent, look for this last theorem. Theorem 9 is always 99.9% of the time going to be there. The theorem states, and you must check this out nicely so that you can get it, that the angle between a tangent and a chord, so there's my tangent, right? So where between the tangent and a chord can be like A1, do you agree with me? Up to the chord. I could have just as well done it on the other side as well, and I'll do it just now. Between the tangent and the chord, right, will be equal to the angle in the opposite circle segment. This is major math language. Well, all that it means is, at the moment here, I'm in this segment, busy with this segment somewhere. So where's the opposite circle segment? Still with that chord. So I'm going to teach you to work with your hands again and say, if this is the angle between the tangent and the chord, go to the chord, take your fingers, go to the other side, which will make an angle B. So those two angles will be equal to each other, and the abbreviation is tan chord theorem. Nice and quick to write that down. Look again. So if it's the angle between the tangent and the chord, and now remember, this is very basic. There's just like 4 lines on the sketch. When it gets complicated, you actually got to go search which ones are going to be equal. So now tell me, what will angle A3 be equal to? C. How do you get it? Between the tangent and the chord is AB, right? So here I go, AB. I'm here, so I need to go there to the opposite side. I'm talking about the opposite circle segment, so it can't land up over here somewhere. Circle segment means it's got to go until the edge of it. In other words, it has to be an angle at the circumference. So it has to be. And it can be skew. There can be lots of skew angles here as well. Let's just do a few so that you can practice. Okay, that's a bit skew, very skew. Let's make it nice and squished into the one corner. C3
equals to A.
Are you with me here? And then C1
Equals to B.
Can you see it? C3, that's your chord going that side. C1, your chord is AC, other side. It doesn't feel like you're going far enough, and that's okay. Even if you had the larger your sketches become, the more kids want to say that A1 is equal to C, maybe even if it was further up there, somewhere there. Then you feel it has to be the furthest one, and it's not. If I'm looking at A1 there, between the tangent and the chord, then I take my fingers to the chord's name is AC. So you go AC and you've got to go this side because it feels too close, eh? So that's what you've got to go look for with your